Thank you. Yeah, so hi everyone, Deej, I'm Alex. And today I'm going to be telling all of you about a new cryptographic primitive, a collaborative zk-SNARK, a zero knowledge proof for distributed secrets, which is something that I developed in collaboration with my advisor Dan about 2 years ago. And in the time since then, collaborative proofs have found various applications in some industrial contexts, and other researchers have also built on them a bit. So at the end of the talk, I'll have some time to talk about future directions and what has happened over the course of the last 2 years. But since we're here ultimately to talk about distributed proofs for distributed secrets, I'm going to start by discussing what it means to prove things in zero knowledge about localized secrets. That'll give us a sense of why we're interested in distributed secrets. So I'll start with an example. Oh, give me a second. Let's get the clicker working. Maybe it's just not working.
There it goes.
Okay, cool. We're good. So why is it important to prove properties about secrets? Well, the first example I'll give is an example that we're all familiar with in security, which is authentication. It's something that all secure systems are based on. And fundamentally, the mechanism that we use in order to authenticate individuals, or I should say authenticate computers, is showing that computer has access to some secret that only the authentic computer would have. So that might be a human showing they know a password that hopefully only that human knows. That might be a computer showing that it has a secret key that only that computer would have. And in this context, of course, one way you can show that you have that secret is you can take the secret, you can hand it over to the server, and the server can check. But if you do that, the server can impersonate you in the future. So we don't want to do that. And that's why it's important to be able to prove that we have that knowledge without revealing it. In this particular context, the context of authentication, the secret, the key or password, is held by one party. And that means that a traditional kind of zero knowledge proof, called the zk-SNARK, which I'll define in more detail later, applies. It gives some algorithm that one person can run to show that they know the secret data. But there are lots of settings where the secret information that's relevant to some problem is not all in the hands of one individual. There are settings where the secrets are distributed. I'll give you a few examples. First, consider a money laundering scenario. There's some entity, Eve here, who has obtained a ransom paid by another entity, Colonial Pipeline. And what I mean by that statement is that in the global graph of all transactions that have ever happened, there's some path from Colonial Pipeline's ransom payment to Eve's current account. If you want to show that this path exists, if you want to show that Eve really is guilty of obtaining these funds, then that means that you need to show that this path exists. But that's a hard thing to do because the global transaction graph is not public information. There's no one entity that knows all the financial transactions that happen around the world. There are different banks and different individuals that are aware of different transactions. And so you might imagine that in this picture, the green edges are transactions that one entity knows about, the blue edges are transactions that another entity knows, the purple edges are, or I guess the magenta edges are yet another entity. And so proving the existence of this path is proving a property about distributed information. Another setting where secrets are distributed arises in the context of aggregate statistics. So imagine, for example, a collection of hospitals that are all following the same pricing rules, the rules that determine how much a given procedure costs. These hospitals might be interested in showing that empirically these rules are not discriminatory. So particular groups defined by race or gender don't end up paying more on average because the procedures that they happen to get are being charged more for. But in this context, once again, the relevant secret data is all of the procedures that were done on all of the people and how much was charged for them. That's very sensitive data. That's data that's held by each hospital. And at least in the United States, the hospitals wouldn't even be allowed to share that with one another without jumping through a bunch of groups. Around the world, I imagine that's the case too. So if you want to show that that data in aggregate satisfies some fairness property, some empirical fairness property, that's a proof about secret data. And I'll give one more example, which I give because this is an example that there's been some industrial interest in, which is, forget for a second about distributed secrets. Imagine that there's just one person who has some secret data and they want to write a zero knowledge proof about it. You might have heard that producing these proofs is often very expensive. So if this person is using a phone, they might not have the necessary computational power to do that in a reasonable amount of time. A natural approach is to outsource the construction of the proof to some other entity. But if this data is sensitive, I don't just want to send this data to the cloud. And so one thing you might do is you might take that data and split it into different secret shares, S1 and S2, neither of which reveals the data, and then send those shares to, well, different servers that are computationally powerful. And now, even though initially our secrets were localized, at this point they become decentralized. And the problem of constructing a proof about them, so it's a problem including properties of distributed secrets. So we've gone through 3 different settings in which you might want to prove a property about secrets. And in one of these settings, in authentication, those secrets are localized, but the other settings, they're distributed. And we need a tool that allows us to write proofs in the distributed setting. And that's what this talk is about. So in part 1 of the talk, I'm going to provide some background on zk-SNARKs, these general purpose conventional zero knowledge proof systems. There are lots of kinds of zero knowledge proof systems, zk-SNARKs are one. And the second part of the talk, I'll introduce our new tool, the collaborative zk-SNARK. I'll tell you about the syntax of it and the security properties that it needs to have. Many of them are inherited from local context, but there are some that are new, and they arise because there are now multiple entities involved. In the third part of the talk, I'll explain the way that we construct collaborative zk-SNARKs, both in theory and in practice. So I'll tell you about the theoretical construction and then also the implementation that we did, because there's kind of a cool hack that went into doing the implementation. And then finally, I'll tell you about the results of that implementation, the experiments that we did. And in particular, the takeaway here is going to be that even though collaborative zk-SNARKs are some kind of distributed protocol that a bunch of different entities run, it doesn't actually take longer to construct a collaborative zk-SNARK than it takes to construct a normal zk-SNARK. So if you're familiar with multi-party computation, this is one example where somehow the multi-party computation isn't actually much slower than the normal computation. So that's the order of events. And I'll take this time to say that if you have questions, you should just jump in at one time. And the reason is that way it becomes appropriate to cut material. I'll know that. Okay. And let's get into it. Yeah, part 1. Okay, so zk-SNARKs, what are they? What are they for? The fundamental object of zk-SNARK is a witness relation, or a set of pairs. We call the 2 elements of the pair, X and W. X is called the instance, it's the public data. Think public key in the context of authentication. And W is the witness, it's the secret data, think secret key. And then the relation, of course, is a set of pairs that are valid. So in some sense, this relation defines a property. Some pairs satisfy the property, some don't. When I say public and secret, we're imagining 2 parties here. The party that knows everything is the prover. The party that only knows the public data is the verifier. And the verifier is wondering whether or not the prover's secret data satisfies the relation, whether it's valid. A natural way to show that it's valid, that doesn't respect privacy, is just to hand over the secret data. You can check for yourself. But there are some downsides to this. The obvious downside is that it's not private. There are also people who don't like this approach because the secret data might be very large, and so checking their property directly might take a while. But for either reason, you might not want to do this. And what a zk-SNARK is it's essentially a layer of indirection that removes these limitations. So a zk-SNARK is a collection of algorithms. It's a set of algorithms along with the proving algorithm and the verification algorithm. The proving algorithm is run by the prover. It takes in the results of setting up the system together with all the data, the public and the secret data. And it produces this proof that you then give to the verifier, and the verifier runs verification on in order to check. So that possible outputs are 0 for this proof is rejected or 1 for it is accepted. The properties that these algorithms need to satisfy in order to be considered a zk-SNARK are as follows. The most basic of them is soundness, which means that this proof should actually show that W exists. Defining that more precisely is a bit more involved. I'm not going to do it today, but it can be defined precisely. And then the rest of the properties that the zk-SNARK needs to have are actually spelled out by the acronym zk-SNARK. ZK means zero knowledge. So this proof should not reveal anything about W beyond its existence. S means succinct, which means that the proof should be small and verifying it should be fast. The systems that are most widely deployed today actually have proofs of verification time that are constant. They're independent to the size of W, but even something that was like square root of W is very good. N means non-interactive. That's actually implicit in the picture that I drew. The proof is just a blob of bytes that you send to the verifier. It's not a conversation between the 2 entities. AAR, that stands for argument, which is actually a relaxation. It's okay if this thing isn't quite sound in the complexity sense. It's okay if it's only sound under computational assumptions. So it's sound against provers that run in public time. And then K means that, this is a somewhat technical condition, that the proof doesn't just show the existence of W, that's called existential soundness. It also shows that the entity that created the proof knows W. It's a bit involved to define what it means to know something, but it can be done. And sometimes this knowledge is important. And as an example of why it's important, let's think back to the application of authentication and see how this syntax and how knowledge maps onto authentication. So here we have the same picture that we were just looking at. In the context of authentication, the client is going to be running the proving algorithm. The server is going to be running the verification algorithm. The public data, that's the public key. The server already has it on the file. The secret data, that's the secret key. The relation here that we're checking is valid key pairs. So the public key and secret key match. And it's important that the proof not just shows that a secret key exists. Some secret key always exists, the match to the public key. The important thing is that the person that you're talking to knows it. So this is one setting where knowledge is important. And once you're convinced that this entity knows the secret key, then you can authenticate somebody. You can provide that proof. So I will make a quick disclaimer here. Authentication is actually a hard problem in its own right. zk-SNARKs are neither necessary nor sufficient on their own to solve authentication. You might worry about replay attacks. Also, zk-SNARKs are sometimes don't perform very well, and authentication has to be super fast. So people develop specialized approaches. But I give it as an example because we're all familiar with it. Right. And it also shows off why knowledge is important. Okay, so this is the syntax of zk-SNARKs. Any questions?
Any application that uses zk-SNARK?
Right now? Yeah, so my favorite application is actually private payment systems. So one thing that I love about, and I usually pay for things in cash because I think credit cards are a little creepy, is that when I give the restaurant cash, like my credit card company doesn't know that I went there. And there are some people who want internet currency that has that same property. So the first private cryptocurrency, Zcash, is built using zk-SNARKs. In order to spend money anonymously, I produce a proof that I know of some money that's never been spent before. And I hand that proof to you along, as well as broadcasting some information that invalidates that particular money in the future. And that convinces you that somebody is spending some new money. Yeah, thanks. Right. So I'm not going to go into the details of how zk-SNARKs are constructed today. We'll learn a little bit about the bottlenecks later when I talk about our contributions to make those bottlenecks reasonable. But I'm going to give you a rough landscape of what consumptions SNARKs and what mathematical objects they're based on. So the first family of zk-SNARKs are based on pairing-friendly elliptic curves. These are the ones that for a long time are the most computationally efficient. So the famous one here is called Grot 16. It was invented by Jan Grot in a 2016 paper published at Eurocrypt. And then there are also more built on a particular polynomial scheme called KZG that uses pairings. So these are some of the terms there. There are also SNARKs constructed from other kinds of cryptographic assumptions. For example, from hashing, from coding theory. So fractals in this bucket, stars are in this bucket. And then there are SNARKs constructed from entirely different kinds of assumptions. Especially recently, there's been a lot of action trying to build them from lattice-like assumptions. That's been going very well. But you know, there are lots of constructions of SNARKs. For the purposes of proving properties of distributed secrets, they all fall short because there's this question: which one entity is going to run the proof? And if the secrets are distributed, there isn't a single entity that can do that. So that's why we needed it. So syntactically, what is a collaborative zk-SNARK? Well, it's a slight generalization of a conventional one. So here's the picture for a conventional one. Proving algorithm gets run on secret data, produces proof about that data, gets checked. In the collaborative setting, we just change the number of provers and the number of witnesses. So in this picture, there are three. Of course, in general, there can be any number. And we say that each prover has their own witness. So PI has witness WI. The idea is that these provers are going to run some interactive protocol among themselves. And the output of that protocol is going to be a non-interactively verifiable proof that can be checked by anybody. So I'm emphasizing this because another reasonable option might be having this verifier individually interact with different groups. I might ask different questions of each of them. So that's not what we're doing here, and it's very interesting. But we want the proof at the end of the day to be non-interactively verified. So that means that when you compare us to the conventional SNARKs, the setup algorithm syntax has not changed, and the verification algorithm syntax has also not changed. The only thing that's changed is the syntax of the proving algorithm is no longer an algorithm, now it's this interactive protocol among the different parts. Okay. So what ramifications does this have for defining security? A lot of security properties are inherited, but there are two that are different in the collaborative setting. The first of them is zero knowledge. And the reason is because now we don't just worry about the verifier learning things or the proof leaking things. We also worry about the other provers that we are interacting with to construct the proof, learning things during that interaction that might be revealed. We would like, for example, an adversary who corrupts provers 1 through 3 in a 5-prover protocol to not learn any information about the secrets of the remaining 2 proofs. So we capture this with a property that we call T0 knowledge, so in some sense a generalization of zero knowledge. And what it says is that an adversary who controls at most T provers should learn no information about no new information through the interaction beyond whether or not the witnesses that were used are collectively valid. So let's take are the two things going on here. First, what about this thing? I said we shouldn't learn anything new except for the fact that the witnesses are collectively valid. That we cannot avoid hiding, or sorry, we cannot actually hide it. And why not? Because our goal here is to create a proof that shows the validity of the witnesses. That proof is publicly verifiable. The adversary at the end of the interaction could verify it. It's going to reveal whether or not they're valid. And this is in some sense just one bit. The whole goal is to show this. So we're okay with leaking that. The other thing about this definition is it's got this threshold. So we're saying an adversary who corrupts up to T of the provers doesn't learn anything. Let's think about different values for T. What if T is everybody in the protocol? Well, if T is everyone in the protocol, so if T is equal to big N, the number of parties, then there's no secrets from text. So this definition doesn't really mean anything there. We don't have any goals in this. But we would like to be able to construct a collaborative SNARK that has N-1 zero. If there's even one honest party, that party's secrets should be protected. And we'll also show some constructions today that achieve a worse kind of zero knowledge. They'll achieve something like N/2 zero knowledge. And the advantage is that they'll be a little bit more efficient. So that's the rough idea of this definition. In a little bit more detail, the way that we formalize this is through the simulation paradigm. So we imagine an adversary who has corrupted up to T proofers, and we require that there should exist an algorithm, an efficient algorithm called a simulator. The task of the simulator is to take in the corrupted witnesses, so all the data that the adversary already has before the protocol runs, as well as X, the public data, so that they have that too, and this validity bit that we are okay with leaking. And the simulator must construct from this a transcript of what the adversary would have seen during the protocol that's indistinguishable from what the adversary would see if it really ran in connection with these honest parties. So this is the standard way of defining zero knowledge, and here we're in some sense like doing, I guess, the NTT version of this, because we're imagining an adversary who's corrupted a bunch of parties. And it's not so hard to construct protocols that are zero knowledge. The second property that changes in the collaborative setting is the definition of knowledge soundness. So this idea that the entity who created the proof knows the witness. The reason this is interesting in the collaborative setting is that there isn't just one person anymore. So what does it mean for this group of provers to know something? It turns out there are a lot of different definitions of knowledge that could apply in this kind of context. One very natural interpretation of knowledge would be that if this proof checks out, then prover 1 should know witness 1, and prover 2 should know witness 2, and so on, through prover n knowing witness n. This is a very precise kind of knowledge statement, but this is not actually what we end up achieving with our abstractions. We obtain something somewhat weaker. The kind of knowledge that we obtain is as follows. you know that the provers, one through n, collectively know the witnesses W1 through Wn. So if you were to take the state of all the provers and pool it, then you can compute all the witnesses. It turns out that this definition of knowledge is not new. In fact, this is studied in an old paper due to Joe Halpern and Yoram Moses back in 1990 called Knowledge and Common Knowledge in a Distributed Environment. And this is actually the term that they call distributed knowledge. This is other kind of knowledge, is something else. So the reason that we get this kind of knowledge, it actually falls out. This is a bit technical, so no worries if it doesn't work for you. We'll come back to the main line of thought in a second. But we do the way that you prove this kind of knowledge is you construct an algorithm called an extractor. The extractor is responsible for computing these witnesses. And the way that you get this extractor to reveal this information, or the way that you get the prover to reveal this information that should not be revealing, is you do this thing where you rewind the prover. You reset it to an earlier state and you run it forward. This is a way of probing the information it has access to. And we do all our proofs in the random oracle model, which means that our extractor is also based on programming random oracles. So the way that you rewind the prover is that you change the random oracle priorities that it was making before. But all the provers are accessing the same random oracle. So you're kind of resetting them all together. And that only allows you to make statements about what they collectively. Putting the formalism aside for a moment, I think a more interesting question is whether it's possible to get a more precise kind of knowledge out of the syntax. Remember, the verifier does not have direct access to the individual provers. For all it knows, one entity simulated this whole proving protocol in its head, and then just came up with the proof and handed it to the verifier. Yeah, it really seems like the verifier can't say anything specific about different entities involved in creating that object. At least not in a general way. I think there might be ways out of this that would be interesting to talk about. If anyone's interested, you can perhaps ask at the end. So anyways, this is the kind of knowledge soundness that we obtain, that we define, and we end up obtaining. And for the applications that we're aware of, this seems like more than enough. And in lots of contexts, this issue of knowledge isn't even really a problem. Okay, so that's what I have to say about security. Before we go on to the constructions, I do want to say a bit more about the syntax. But maybe I'll pause here in case you have any questions on security first.
So when you combine the knowledge soundness definition with the goal of having TEN-1, you do end up still with each party needs to know something that is not known by anyone else, right? Like in order for TEN-1.
Yeah, I think if I'm understanding the question right, unfortunately you don't. And the reason is you certainly establish that like every part of the witness needs to be known for sure. Absolutely. And I think that's very much related to what you're saying there. But it still could just be one entity simulating all of the provers in its head, knowing all the witnesses from the get-go. Yeah. Yeah, I think if you're trying to do something else, you would need like some notion of identity baked into the syntax of verification somehow. Like the entity with this public key contributed in this way, and the entity with that public key contributed in this other way. Yeah. It's a good question, and also you should take my answer with a grain of salt, because we haven't really formalized some of these alternatives. So I think it's fair to say we don't totally understand this one. Okay, and let's talk about.
Sorry, is there a use case for the first definition that said for knowledge soundness that we could prove that P1 only P1 knows that we want, something like that? What could be the use case?
Yeah. So let's think about that for a second. So riffing off of this example of authentication that I gave earlier, you might imagine this would be sort of a weird setup, but you have a bunch of parties who want to access either a single server or perhaps a collection of servers. But the channel, and while the parties have good access to one another, the channel from the parties to the server is not so good. Maybe we're trying to connect to the space station. And so if there's some way of perhaps bashing the authentication, that could be quite useful. And this could be a tool in achieving that. Yeah. But to be frank, that's a little bit of a weird application. It seems like a lot of the time existential soundness is enough, so knowledge is not even an issue. And even when knowledge is important, perhaps it's not so important who exactly knows it. It's a good question. Yeah, I think it's an interesting one, but it's kind of a cool technical logic, like what needs to know things. Yeah. If you have ideas over applications, I'm always Okay, so now let's talk about not the security, but the concrete syntax. So far I've been very fuzzy about like, there's like some predicate, there's some witness relation, and we're going to prove membership in it. I'll be more specific now about what I mean there. So specifically, we're going to focus on a particular class of witness relations that are NP complete. The class that we focus on is not a new class, it's one that's used by traditional zk-SNARKs. It's called R1CS, or rank 1 constraint system. So the most important things that you should know about R1CS are first, well, yeah, it's a class of relations that's NP complete, and second of all, it generalizes arithmetic circuits, which is why it's NP complete. So like if you don't want to worry about the details, you can just have in your mind that this relation is defined by some circuit that outputs 1 or 0 for either membership or non-membership in the relation. But if you're interested in the details, the way that this relation is, we say, arithmeticized, is that there are these 3 different matrices, A, B, and C. And the witness and the instance are these 2 vectors, x and w, whose length, when you concatenate them, is n. So they're called concatenation A, the assignment. And the relation is satisfied when big A times little a, category product, so all product, with big B times little a is equal to big C times little a. To see that this is somehow an arithmetization of the arithmetic circuits, you can imagine that the multiplications in the circuit are going to be captured by this category product, and any additions or other linear operations can be captured by these matrix multiplies. So you look at your circuit and baseline your circuit, you can do these matrices. So why do we use this? This is an arithmetization that's already used by conventional zk-SNARKs. And when I say in this work that we construct very efficient collaborative zk-SNARKs, more precisely, you can construct very efficient collaborative zk-SNARKs for R1CS when the witness is shared in a particular way. So the specific problem that we study is we said, okay, we've got this R1CS relation, so we've got A, B, and C, and we're going to assume that the witness is a secret share among the servers in some fashion that, according to some secret sharing scheme, that's going to be defined by the collaborative zk-SNARK itself. So we're going to give instructions to these zk-SNARKs. Each SNARK will have a secret sharing scheme, and you need to distribute the witness in that way. Great. So what exactly are we assuming when we adopt this focus? We're assuming that there's some kind of pre-processing phase that translates your relation and your witness into this one. So in terms of translating the relation, that means that you've got some kind of compiler that's mapping some higher level language that is understandable down into these matrices. And that compiler also produces what's called a witness encoder. It takes the witness in its original form, so like a field element that is an ECBSA secret key, and then turns it into the W and the X that you need for these matrices. So there are in some sense 2 different kind of pre-processing that have to happen. You have to do this offline compilation, you have to do this online witness encoding. The offline compilation, that's like very standard. You're going to build a compiler to do that. You're going to, in fact, probably use exactly the same compiler that people are already using for normal things. The witness encoder, though, is a little bit different. And the reason here, traditionally, the witness encoder is some algorithm that I run locally before constructing my normal SNARK. But now the secrets are distributed. So the witness encoder is actually going to be a multi-party computation protocol. The output of it will be this secret shared witness. And then once you have a secret shared witness, then the problem is the problem of this talk again. How do you build a proof problem? So actually we'll pause here, yeah.
How is the T and the T0 knowledge composed with like the threshold in the threshold secret sharing scheme that the protocol uses? Yeah.
That's a great question. So okay, great. So first of all, you cannot possibly be more zero knowledge than the secret sharing scheme is hiding. So better is not possible. For the instructions that we give, they match exactly. There's no like rule about that, I guess. That I can think of right now. Yeah. But yeah, so you should think. So like I said, we're also going to take n-1 and n/2 zero knowledge, and that will come from secret sharing schemes that use those thresholds. Okay. Other questions about, I guess, this division of responsibilities that we're adopting? Like we're not good. Okay, so now how do we construct these things? And here, actually, I'm going to pause and ask for suggestions from the audience, because I think one of you is going to suggest exactly the beginnings of the right idea. So how would you do this? You got a secret shared witness, you want to create a proof of it. The more naive, the better.
Okay, so naively, I'm imagining each person constructs a proof of their share and then you combine them together somehow.
That's fantastic. Yeah, good. So the idea is I prove something about my data, you prove something about your data, and then we combine it. Good, good. And in a lot of situations, this isn't going to be exactly the right thing to do. In particular, if our predicate is really a conjunction of predicates, a predicate about your data and someone else's data and someone else's data. I think this is just the right thing, and you should do it. And of course, the challenge that arises is that maybe it's not a conjunction. And so then the question is, how exactly do you split up this predicate? And there might be a way to do that cleverly. Yeah. Yeah, it's not calculated.
Okay, so what if we combine data somehow
Yeah.
before proving it and then
You combine the data and then prove it. Yeah. So no, it's an idea. So then the question is, how can you combine it? How can you combine it in a secret sharing way? Yeah, I mean, a good option here, especially for folks who like to work on TEs or trusted hardware other way, perhaps you're going to send all this data to some kind of enclave and then construct it there. And there are always interesting questions there, like these enclaves are low memory and some of these proving algorithms are high memory. Maybe you can get them to work with it. That would be a good question. Yeah. Okay, I think you guys are too clever. So the starting point here that we start from is even more naive, which is there exist these things called MPC, multi-party computation protocols, that will evaluate any computation you want over secret shared data. So why don't we just use them? So here's the pitch. So we're going to take this generic MPC protocol, and the function that we want to evaluate is the proving algorithm. And our data is secret shared, like I said. So you can do this, but the concern with going this route is that it might be very, very slow. If you know anything about these kinds of programmable cryptography, SNARKs, and MPCs, they often are much slower than the underlying computation that they're trying to simulate. So SNARKs, just to give you like some rough number, are typically 1,000 times slower. Building SNARK is 1,000 times slower than checking the property of the theorem. And MPC protocols are known for having similar overhead. It's oftentimes 1,000 times slower to evaluate the protocol in a secure distributed fashion than to just run on your computer. And so the concern is that if you compose these things, you might end up with something that's like 1,000,000 times slower. And maybe there's some applications that are taking 1,000 times slower. Like something's taking a microsecond. I don't really care if it takes a millisecond. But 1,000,000 is long. And so fundamentally what we do with this work is we show that you don't have to get this kind of multiplicative law in overhead. You can actually get an additive law in overhead instead. So you can end up with something that's more like 1,000 to 2,000 times slower. And you get this by doing this composition, but by doing this composition carefully. By tailoring the MPC so that it can perform the kinds of operations that the SNARK needs to do quickly. We can come back to it at the end, but really the idea that the overhead is additive is actually a perfect good. In some sense, maybe you run the MPC first and then you build a proof after and it takes about the same time that you did wrong. Okay, so anyways, how do we get this? So the way that I'll explain it is by just talking about the different kinds of things that happen inside a SNARK that either are classical bottlenecks or might become a bottleneck in the distributed setting. And I'll tell you about some of what we do to make some of those bottlenecks non-bottlenecks. So I'm not going to walk you guys through the whole description.
Yeah, question. So first, I'm not an expert in this area, so this may be a dumb question.
No questions.
In your previous slides about the knowledge, collectively knowledge, especially, so you assume that all the parties collectively know the whole thing.
Sure.
Can I say that for MPC, I can assume that the first one, which is one party knows one.
Yeah. Okay.
So if I apply this naive composition of the two things, will I get the same? Will I get the first thing that each party not only knows its own part, but at the expense of super heavy slope?
It's a great question. And if you do the composition naively, you will not get that kind of strong knowledge. And the reason is because at the end of the day, this MPC protocol is going to produce a single object, the proof, and then you're going to hand that proof off to the verifier. So even though multiple parties like interact with each other to construct the proof, the verifier doesn't have direct access to it. So it cannot make statements about who knows what.
I see.
It is true though that like if a collection of people participate in the MPC, the people who participated might know something more about who's involved with what.
I see.
Yeah. It's a good question. I think it also suggests like a line of inquiry. We might say, okay, what happens if we actually allow the verifier to participate in this interaction? Maybe we can get something more fine grained. Maybe you have a verifier participate in a very lightweight way. Yeah. Okay, so let's talk bottlenecks. So I said I wasn't going to go through the full construction of a snark, and I won't. But I'll tell you about like some of the heaviest hitters, these heaviest hitters for CPU. So the classical bottleneck in these elliptic curve-based conventional snarks are the elliptic curve operations. There are a lot of them. And in this talk, I'll explain a technique that we use to make these very fast in the distributed context. Not faster than they are locally, but not slower either. Or at least not much. Another heavy hitter in constructing a classical snark is computing Fourier transforms over a finite field. So which of these, the curve operations or the Fourier transforms is faster depends a bit on like how big the snark is. The elliptic curve operations scale sublinearly in the size of the circuit, and the Fourier transform scales superlinearly. But somehow the elliptic curve operations are concretely worse, so eventually there's a trade-off. It turns out that so these Fourier transforms, they are slow. But there are lots of multi-party computation protocols that operate over finite fields that are extremely efficient on linear operations. And the Fourier transform is linear operators. Maybe you learn in your signal systems class. So this is just sort of like not a problem how it works. You won't get any slower in the distributed. The next thing to think about are things that might become bottlenecks once you start to distribute them. And the first thing to look at here are, so they said that linear operations are very fast, but all the nonlinear operations that are going. So first you might think, okay, these snarks, it turns out they're built on terms of polynomial arithmetic. There are some polynomial multiplications and divisions. Maybe those are going to be slow. It could be a problem, but it turns out that snarks will do polynomial divisions. They always divide by public polynomials. So if you view the operation as an operation over secrets, it's actually a linear operation. This is something we can show. One other thing that some snarks do is they compute sequences of partial products. They have a whole bunch of field values, and they want the product of the first two, the first three, the first four, the first five, so on. This is an honest-to-God nonlinear operation, and it's even the worst kind of nonlinear operation. It's very sequential. It's very deep. Multi-party computation protocols don't like that, but it's also a very specific operation. It turns out that there's like a protocol from the 90s that does just this: sequences of partial products. And it does them very, very quickly. Yeah. And that actually has a constant number of rounds of interaction. Another challenge that comes up in the context of these hashing encoding based snarks is hashing, specifically evaluating local trees on lots of data. As you probably know, hash functions need to be collision resistant, which means they have to be highly nonlinear. Otherwise, they wouldn't be collision resistant. And we don't really have a good fix here. So I'll tell you about the best idea we have, which is pretty bad. This is a direction for future work. So ultimately, the way that we leave the literature is that if you've got one of these elliptic curve-based snarks, or at least for lots of elliptic curve-based snarks, we have great ways of making it collaborative. And for the hashing-based ones, fit it. Okay, so order of events. Let's talk about elliptic curves inside snarks, and then let's talk about hashing. So first things first, elliptic curves. I'm going to give a brief MPC crash course so we can understand how we can make the elliptic curve operators fast. So fundamentally, these generic MPCs that the ones that we're going to go on, the algebraic ones, they're tools for evaluating arithmetic circuits. Now, I really do need an arithmetic circuit. So you've got some kind of directed acyclic graph. You start off with some inputs, you've got gates, they multiply, they add, and then you've got some output at the end. The way that most generic MPCs are constructed is based on secret sharing. So the MPC starts by taking the inputs, which might be held by different parties, by party one, by party two, by party one again. And those parties distribute their data among all the parties, among all n, according to some secret sharing scheme. So on this slide, I'll show you additive sharing. where X is represented as X1 through Xn, which are all sampled uniformly at random, subject to the constraint that they sum X. This is a secret sharing scheme where you need all n values to recover the secret. So the threshold is n minus 1. So the way that the NVCs they start by secret sharing these. Okay, so you've got secret sharing inputs, and then what the protocols do is every MVC protocol defines its own subprotocols for evaluating additions and evaluating multiplications over secret shares. So some protocol for addition, some protocol for multiplication, and use these protocols to work your way through the circuit. So you apply the addition protocol to sum x and y, or to come up with shares of the sum of x and y, and then the multiplication sub protocol as well. And then once you've got shares of all the outputs, you reveal the secret shares to everyone, and everyone learns the outputs. Or maybe if you want some parties to learn, you reveal the shares just for its parties. Great. So this is so this is it. Okay, so the two specific MVC protocols that we start from are called speeds and GSC. So they're different and they're similar in some other ways. So the way that they're similar is that for both of them, addition is super cheap and multiplication is expensive. That's the common reference. But the way that they differ is that they differ in terms of efficiency and also in terms of the threshold for which they are applied. So speeds can work no matter how many malicious parties there are. There are n-1 malicious parties, speeds will still work to still protect your data. GSC assumes that the majority of the parties are honest. So it's only secure against n over 2 corruptions. And the trade-off is that GSC is about 2 times faster than speeds, almost exactly 2. And the reason somehow is that the way that speeds works, I should say neither of these use additive sharing. They both use more complex sharing schemes. But in the context of speeds, it actually uses shares of the data and then also shares of some message authentication code applied to the data. And the whole computation has to be duplicated over the MAC, the authentication code, and over the data, so that's why it's 2 times. Great. So these are the two protocols that we're starting with. And you choose which one depending on the value of T or your collaboration. So how do we use these to elliptic curve? So elliptic curves, well, you know, they're just like XY pairs, where X and Y are from some finite field. There are some other ways of representing them too, but we don't have to worry about that for today. And there's some elliptic curve operation, some way to add these pairs of points together. And there's just like some formulas defined over the coordinates for how you do addition. So that you apply. So the first question, of course, is how are you going to represent these in the multi-party computation? And the natural way, of course, since multi-party computations work over fields, and since these x's, the x's and the y's are from the field, is to secret share the x and the y. And that does work. So, you know, I've got my x shared or my y shared, I've got my other x shared or my other y shared. And in order to do an elliptic curve add, I evaluate the formulas. And the formulas are defined in terms of addition and multiplication. So I use the, the MVC subprotocols for that. And it does work, but the problem is it's quite slow. And in particular, these formulas, even the formulas for elliptic curve addition, involve lots of field multiplications, typically between 3 and like 8. So that means that these elliptic curve additions end up being quite expensive. And if you do end up taking this approach, this leads to the million-fold slowdown that I was warning you guys before. So we don't do this. Instead, we do something else. Instead, we observe, hey, typically people do MPC over fields, but you could also do MPC over rings, at least over certain kinds of rings. And in particular, you can do multi-comp the MPC over the elliptic curve points themselves. So instead of representing the secret shares of G as the secret shares of its coordinates, I could represent G as n different elliptic curve points that sum in the elliptic curve sense of the word up to G. Different data representation. And if I take this data representation with additive sharing, and I want to add shares of G1 and shares of G2 to get shares of their sum, then every party can just locally do that addition on their own shares. Of course, as I said before, the MPC protocols that we build on, they don't use additive sharing. They use other kinds of sharing, specifically authenticated additive sharing and severe sharing. But this is the same idea applies to it. So you can come up with some protocols for doing elliptic curve additions that don't require communication between the parties. And moreover, you can come up with some protocols for multiplying elliptic curve points by finite field elements that are very about as efficient as a field multiply in a standard MPC. Great. So yeah, this is what we do, and this makes the elliptic curve stop super fast. So it turns out that the bottleneck, so the elliptic curve operations in the SNARK, the bottlenecks are these things called multi-scale multiplications, and they're actually linear as a function of the squares. So linear in the elliptic curve sense. So they're like lots and lots of additions in curve points. So this means that there's essentially no for the bottlenecks. So there are some multiplies that happen, and it's good that we have a protocol for that, but they're not involved. So SNARKs, they're almost linear in the elliptic curve, which is quite helpful. Okay. Yeah.
Question, you mentioned that option to you use NPCs that work over rings. Okay. What is the ring that you're using?
Oh yeah. So we're sort of That also is not very precise in stating. So we're going to run the NPC over a combination of field elements and group elements. And here we're really treating the group as like a group module. So you can multiply elements in the group by elements in the field, which is like just like doing repeated additions, the equivalent to that. Exactly. And it's a question for every NPC whether you can use it in this way, but for speeds, folks have actually already observed you can do this. And for GSE, we showed it this was. Okay. So let's talk about hashing. We're specifically doing these Merkle trees. So broadly, the way that this works is that the SNARKs that are based on Merkle trees and on coding theory, what they do is they take this representation of the witness, which somewhat confusingly here I'm calling this, and they build a huge Merkle tree. And the problem is that in our context, that witness is a secret shared. So here we have different parties. Here we have different parts of the witness. And that means that these hash functions, well, they're being applied to secret shared data. And the hash functions are highly nonlinear. This is exactly the kind of thing that leads to that millionfold slowdown. And importantly, hash functions, unlike elliptic curve operations, hash functions are not very structured. In fact, they're sort of specifically not structured. That's the whole idea. And so basically here, we really don't have very many good ideas. So I'll tell you the thing that you could do, and this is kind of speaking to the approach that you articulated earlier. What you can do is you can have every party commit to hash its own shares. So I will build a Merkle tree to my shares, and you will build a Merkle tree to her shares, and so on. And then we can treat the concatenation of all these Merkle trees as some kind of representation of all of our data. And this essentially works. So then when we want to do opening proofs, when we want to get something out of a Merkle tree, we all do an opening proof against our share. And that reveals like how the sharing works for that particular element, but we're revealing the data anyways, so that's okay. And it's the job of the SNARK to make sure that that revealing is not going to compromise the overall witness. The downside of this approach is it blows up the proof size and the verifier work by a factor of 10. Because now, whereas before we had one Merkle root, now we have 10, and then all the opening proofs are with it. So this doesn't go so well. Of course, you can switch it down. You can do like proof composition. You can take a big proof and then take a small proof afterwards. But this kind of recursive proof composition, while it sounds nice in theory, it doesn't work so well in practice. Just because like the overhead of representing the SNARK verifier inside of the SNARK is a bit intense. So this is basically all we got. And I think this would be a good place to have a better answer.
So now it's computationally like feasible, but the proof size and digital communications is downside.
Yeah, exactly. Yeah, proof size is the bigger, which might be fine. You know, if you don't have 10 isn't very big, no big deal.
Exactly. But you actually have a combination is also hard.
Yeah. So if you want to do this for first, so one way you can get rid of this blow up is by then writing a proof about this constant size machine, and that composition you can do. Although this product is of course small. Okay. My personal opinion, I think hashing is probably just like dead in the water here because it's so unstructured. That's the idea. But I think that some of these lattice-based SNARKs might be a way to get post-quantum collaborators in case SNARK doesn't have this kind of because lattices are like okay, so that's the overview of the constructions of the theoretical side. And I'm going to speed up a little bit because I'm going to explore here. So let's talk about the implementation. We actually did code up almost all of this. We coded up all of the elliptic curve-based SNARKs that we described. So specifically one that's based on Groth16, Marlin, and Flock. And we coded up both the honest majority and the malicious majority versions of them. So n over 2 and n minus 1. So that, that was our goals, right? We wanted in some sense like 6 different collaborative zk-SNARKs across product. So more specifically, what were our goals? At this point, we believe that collaborative zk-SNARKs should be just as fast or 2x slower in the case of speeds than the conventional ones, and we wanted to prove that. So, and we also wanted to prove that in a way that people would believe us. We didn't want to like have our own bad Snark implementation and compare against it. We wanted to beat the state, we wanted to compare the state. So compete with the existing ones, which are very well optimized. So that's a challenge, right? We knew that we have to iterate on like the way the sub protocols for this like partial product thing work and the way that we look at the curve MVCs work. So we knew that the MVCs would need lots of iteration and optimization, but we wanted to try to reuse the existing Snarks. And of course, as always, we didn't want to work very hard because we're lazy grads, or at least I'm a lazy grad student. I don't want to discourage anybody else. And we actually did find a way to meet all of these goals at the same time. And the way is like a clever hack. The hack is based on an opportunity, which is that there's this code base called Artworks, and it is just very modular and very well designed. So Artworks is like a library for implementing Snarks. It's got a bunch of Snarks implemented already. The way those Snarks are implemented is they're all implemented generically over the parent-friendly elliptic curve, which is this pairing engine thing. So like that's like in Rust, it's like pulse and traits, so it's like some interface for all the things that you can do with the curve, and then you define the prover generically on that. And the reason that they did it this way is that elliptic curves are an active area of research. People come up with new ones all the time. If you get a better elliptic curve, you want a better Snark, so you better be pluggable. But we didn't really have any ideas for how to do better elliptic curves, but we thought this level of indirection would be useful for something else. So in particular, what we did is, okay, we're going to cut the connection between the Artworks prover and the Artworks curve. We're not going to wire them off directly. Instead, what we're going to do is on top of the Artworks code, we are going to implement MPC protocols. So we're going to implement MPC for elliptic curves, building on like some network layer and then building on the curve and the field elliptic they already have. So we've got that. So now we've got some code that like, I run on my computer, someone else runs on their computer, we just talk to each other, they do the protocol. Then what we did is we took that protocol, we wrapped it up inside Artworks curve interface. So now what we was like, okay, I've got something, it's like the curve, but actually it's really just a secret share of the curve point. And when I say add, and if you say add on your computer at the same time, then that protocol runs. And then once we had that, we just sort of plug that into the existing groups directly. And the surprising thing is this basically works. You have to mix a few things here and there. This essentially works. So anytime the prover say add, you want to distribute protocol, anytime they say multiply, you want to distribute protocol, and so on. This, of course, this is not something that can do for any computation. Like if the prover said, look at bit number 5, we can't do bit number 5. But it turns out that provers don't want to multiply. They add and they multiply. So anyways, yeah, so via this approach, we were able to take the existing Artworks implementations of Drop16 and Marlin and turn them into collaborative implementations. And Artworks at that time didn't have a Plonk implementation, so we did one really fast. And then once we did it locally, and once we had a global version, we got the collaborative version. And then we did a bunch of experiments based on it. Things that we varied, we were interested in wall clock proving time, we varied the number of provers, we varied the size of the R1CS instances, we varied the capacity of the links between the provers, so how good the network is, we varied the base snark that we were building on, and the mechanism that we're using it to turn it into a collaborative snark, which corresponds to the zero knowledge threshold. And we made a number of simplifications. We ran every local program single threaded just to keep the measurements easy. Usually you would run multi-threaded locally. We didn't do MPC pre-processing. If you do MPC, you should be skeptical, but actually it turns out that the kind of operations that we're doing here are actually quite heavy computationally. You can do a back of the envelope computation that shows that for this particular for SNARKs, this pre-processing is very cheap, which is nice. Basically, because they're pretty close to linear already. And then we did this witness encoding thing, like I said. It's highly property dependent, so it's hard to evaluate generically. So I'll give the basic experiment. So this experiment is there are a small number of parties and the network is great. Okay, so this is kind of the dream. But the thing that we're going to make hard is we're going to make the property really big. So now we're talking about a circuit with a million gates on the right hand side. So this is our single prover baseline, and it takes longer when the thing is bigger. And here's our 3 prover baseline with security against 1. And what you see is, yeah, there's a lot of overhead when the computation is really small, and the whole thing is taking I guess this is like tens or hundreds of milliseconds. But once the computation gets substantial, it's essentially no overhead, which is exactly what we're predicting. And if there are 3 provers with tolerance against 2 corruptions, or 2 provers with tolerance against 1 corruption, you end up with almost exactly 2x overhead. And this is the 2x of duplicating the computation over the MAC of the data. This is all for draw 16. We do the same thing with Marlin and Plunk and get the same results, although those SNARKs have a different baseline speed. But this is the trick, right? This is when the network is great, there's only 2 or 3 parties. We also did experiments when there are many parties. And what we see is that the overhead modestly increases. And so here, we're measuring slowdowns, so we've sort of normalized by the baseline cost of computing the proof. And by the time you have 32 parties, you have an appreciable amount of overhead, but it's still not a showstopper. And there's actually an interesting thing that happens, which is that high numbers of parties, the more secure protocol speeds is actually outperforming the less secure protocol. Perhaps that less secure protocol could be made more efficient at large numbers of parties. So it will be an interesting direction for research. We also did an experiment where we stopped the 2 provers, but we made the link really bad. So here we're talking about megabit speeds and tens of megabits, and this is, I guess, 64 megabits. And what we're seeing is as you get down to megabit speeds, the slowdown grows, but it's still not crazy. We're still not talking 1,000-fold overhead, which is what we typically see. We're talking about the tens or something like this. Cool. So the broad message here is that if you have a small number of parties, constructing a proof collaboratively takes about the same amount of time that it does, which is a really good result. Okay, so what I will say is that this whole thing of like outsourcing, this application that I gave at the beginning, lots of other people have been doing research on that, and I don't have too much time right now, but you should look into that research. It's good research. So folks coded this up with like a phone outsourcing to the cloud and got really impressive speed ups using this kind of technology, which is fantastic. And there are also folks who've been asking, okay, let's say you have a lot of proofs. Is it possible for every prover to work less hard than one prover would work on its own? Like maybe you can somehow distribute the work among them. It turns out that that actually is possible. There are some caveats. They don't know how to do it in a maliciously secure way. Your security threshold gets worse, but it is possible, which is kind of cool. And there's opportunities to do better there. And there are also some other cool opportunities more on the theoretical side. So, you know, when link is bad, communication really does become a bottleneck. And unfortunately, we showed that in some sense this is actually kind of unavoidable. So specifically, the communication needs to be at least linear in the size of your constraint system, and that's because of some reduction to the 2-party communication complexity of an old problem called disjoint. There's maybe an opportunity here to try to improve this bound. In particular, disjoint is like a bit problem, and we're applying it to this field issue that we're facing, and there's some like looseness in that reduction from bits to field elements. I think it would be interesting to try to like study the analog, like some kind of field analog of disjoint, and use that to get a better bound here. And then there's the whole post-quantum thing that I mentioned earlier. Okay, so anyways, I'll stop here. If you forget everything else about this talk, you should remember 3 things. First of all, collaborative proofs support distributed secrets. Zero-knowledge proofs are distributed secrets. That's what it's all about. Second, you should remember that even though oftentimes distributed protocols are very slow compared to local algorithms, that's not the case here. The speed is really quite comparable. And that opens up some doors for what you could do with this technology. And then the final thing is, typically MPC is a lot slower than local computation. That's not the case here. It's not the case because the cryptography we're building on is very structured. But lots of cryptography is very structured. And so, it's an interesting question what other kinds of crypto systems could be made collaborative with similarly good results. I bet a lot of, in some sense, like maybe all of threshold cryptography is already a version of this. Anyways, thank you very much. Thanks for the questions, and I'll do my best to answer the final ones you have.
Hi. So back to the technical part about the knowledge summit.
Yes.
So shows that everyone collaboratively knows the knowledge.
Yes.
The knowledge. So what happens is that one for one of the parties is like actually don't know knowledge, don't know their part of the knowledge. Without that, protocol just autos.
Good. Okay, that's a good question. So I think there's like a few different sub questions here. So one is like, First of all, like what guarantees do you give about the protocol continuing or halting if some party is deviating from the protocol? Right.
Okay,
So like a liveness question, and the answer is we give no guarantees. So if some party is behaving maliciously, they do have the power to abort. They don't have the power to like learn other people's secrets. They can stop.
So actually, my previous picture can be divided into two parts. First one is that knowledge is like the malicious party they have no knowledge at all.
Sure.
And the second is like, for example, the secret share is cracked.
Yeah.
But then for the program afterwards, they
Yeah.
debate. So I think for the second part is like guaranteed by the threshold, as long as the number of threshold parties, as long as the malicious parties don't exceed the threshold. But for the first part, that's the part we does not.
And even a special thing, it says nothing about the ability to finish the protocol. It just says that that party won't learn anything. It's strictly a zero knowledge. Yeah. Also, it's worth noting that the whole soundness thing, that's like totally independent of the threshold. There's no non-collision assumption behind the soundness. And then, yeah, if someone just like doesn't have information, then in some sense the knowledge soundness, if like the information is not possessed, the knowledge soundness tells that the protocol will not finish, right? Yeah. Because like that would imply that it's possible to complete without that knowledge. Yeah.
Yeah. Sorry, can you say a few words about what you meant about like this like communication complexity of this stringness of NFPX?
Yeah. Sorry, I went to super fast. Good. So like this join is the question: you have a bit string, I have a bit string. Do we have any bits that are both one and the same index? And there's like a reduction that you can do from that problem to building a collaborative proof, which is maybe not so surprising because collaborative proofs for R1CS are very expressive. But in that reduction, you take these bits and you in some sense cast them to field elements, so their size blows up, and that's why we get this omega n bound instead of like omega n times field size. I see. And so my suspicion is that you can't this downloads. The question is how to prove it. And the way I would go about proving it is I would look for something that has hard randomized communication complexity. That's the problem that's defined over a finite field naturally. And so like, some things that you might try, like you have vector field elements, I have vector field elements. Is there any index where our field elements are inverses of one another or something like that? I don't think that particular one will work, but it gives you a sense of the kinds of problems we define. Yeah, to my knowledge, this is like obviously not going to focus for communication complexity. They sort of like the bit world. They tend to stay in it. But if you had a field problem, you might be able to get that out.
I feel like this may somehow be related to this like polynomial identity testing.
Yeah, so polynomial identity testing is exactly the case where like the communication complexity is super low. Yeah. So we want like something like the opposite of that. Yeah, exactly. Yeah, so in some sense you have to design the problem so it's like as far from identity testing as possible because
We don't have any questions online currently. Yeah, just say Happy with strings in the CrySP lab if people want to try this. Thank you.